recording. And kick it off here. My name is Shannon McKenzie. I'm one of the co-leads of the Network for Ocean Worlds Research Coordination Network, or now RCN. This is the first episode of the next season of our quarterly lecture series. And we're doing it a little bit differently this time, where we're not being quite so quarterly, because we are excited to celebrate the recent launch of Europa Clipper in this past October. To celebrate Europa Clipper, to mark it the beginning of its amazing journey, we wanted to take a step back and look at some of the investigations that Clipper is planning to do once we get to Europa in the 2030s, and compare that with some of the investigations that are going on now here at our own ocean world, because there's a lot of complementarity in the kinds of measurements that we're making at Europa versus at the Earth, and there's also complementarity in the questions that we're asking. And we might not always get to the answers of those questions through the same routes, so we thought that this would be a really great framework for us, the Network for Ocean Worlds, to investigate together as part of this lecture series. So today, to kick us off, we have two excellent talks lined up. They're going to aim for about 15 minutes each, and then have about 5 minutes for questions each. And then we'll kind of open it up for a more general discussion at the end. First up, we have Dr. Marco Tedesco from Lamont Doherty Earth Observatory at Columbia University. Dr. Tedesco is a planetary scientist interested in seasonal snowpack and ice sheets, as well as global climate change and climate justice. He has led multiple fieldwork expeditions to places such as Iceland, Greenland, and more. Dr. Tedesco is also an adjunct scientist at the NASA Goddard Institute for Space Studies, affiliated with the Data Science Institute, a lecturer at the School of Professional Studies at Columbia University, and is a fellow of the Explorers Club. Marco, take it away.
Thank you so much, Shannon. Please let me know if you cannot see my screen. You should be able to see the entire presentation, the full screen now. Can you confirm that?
Yes, looks good. Thanks.
And Shannon and everybody else, thank you for having me. And Zibi, it's a very pleasure and honor to be, opening this talk where you're going to talk about Europa Clipper. It's also my privilege to open the 2025, and I'm going to talk to you serious, and I'm going to talk to you about cryoconite. I'm going to start my timer so that I'm going to try to make it within 15 minutes. I'm going to talk to you about cryoconite holes. Also, I would like to invite all the exoplanetary scientists to eventually reach out. We did have some projects in the past looking at Mars, but being an Earth scientist, I felt a little bit isolated. I didn't have reached out to the community. So this is a great opportunity for me also to plea eventually potential collaborations in the future. I wanted to thank also the sponsors along the years, the His and Simons Foundation, the National Science Foundation, and NASA for funding part of the results that you will see here. I'm going to start very quickly to give you a very quick overview of the ice on Earth. Then we're going to talk about the dark side of Greenland, the processes concerning cryoconite and their dynamics, the impact on albedo and melting. This is the reason why we care about it, and how this can be folded into exoplanetary studies, and what drove my interest also in this. I don't have to tell you that there are two major ice sheets on Earth, but the reason why we look at them, and I wanted to put the two giants in perspective. Often we hear that they're big, but we fail to capture the size of it. Just to give you an idea, Antarctica, which is here, is as big as probably the surface of China, slightly smaller, and slightly bigger, and smaller than the Russian territory. And Greenland is actually down here on the bottom left, and it's similar to the Dominican Republic of Congo. So there is a big difference. Antarctica contains about 65 meters of sea level rise equivalent, Greenland 7, and we'll talk more about a little bit this soon. Telling you why we're interested in this. Greenland and Antarctica, they've been losing mass, contributing to sea level rise starting in 2002, even before, but in 2002, we have measurements. We can weight literally the ice sheets from space and understand where and how much mass has been lost. Greenland is losing mass at about 270 gigatons per year. To give you an idea, 360 gigatons is 1 millimeter of sea level rise equivalent. The health is true for Antarctica. It's also true that the portion of Antarctica on the west side here that you see, and I'm going to be playing this again for you, it contains as much water as the old Greenland ice sheet. And there is a lot of consequences that can accelerate the melting there. But my job today is mostly focusing on the losses in Greenland and why we care about cryoconite. I call it the dark side of Greenland. People who have not been on the ice, who don't know the ice, they think that, or they might assume that the ice is this beautiful, pristine landscape. In reality, there is a lot going on there. You can see already from this image that, which I removed the scale on purpose, but you can see a lot of brown, reddish, darkish patterns. And this is basically the soot, dust, organic material that deposits on the ice and affects the energy balance. So how well the ice can reflect or absorb the solar radiation, which is the major driver of melting for Greenland during the summertime. The sources of this material can be multiple. In this case, for example, this is Kangerlussuaq, basically on the west coast of Greenland. There is a lot of locally transported material that is deposited on the ice. And then, as we will see, it promotes the formation and the evolution of these cryoconite holes. In other circumstances, the deposition can occur from precipitation, either solid or liquid, and is captured from the atmosphere, of course, and it does its nuclei around the snowflakes using as a nuclei, and then when the snow deposits on the ground, it releases this material. And then you can have landscapes like this one, in which you have, again, the ice, the dark side of Greenland. This is very much true on the edges. In the interior, we do not have this kind of strong contrast. The deposition fluxes are very small there. But the other landscape that you can imagine here is also, you see these dark black patches, very big. Just to give you an idea of the scale, the side-to-side distance is about 300 meters in this case. So we're talking about really pretty big patches of this dark material that is driven, again, by the deposition of soot, particulate matters. Some people, and we also found radioactive materials, anything that you can think in the atmosphere that can be captured through precipitation, it is deposited here, and it's stored on the ice and in the hydrological system. So this is to give you an idea. You have the cryoconite holes that develop once the material is deposited on the ice, and I will tell you in a second how they develop and why they're important. They can assume different shapes and different aspects. The one you see here on the left is, oops, spoiler alert. The one that you see on the left is, now this is not going it's really, it's on the Antarctica, where there is the ice lid that is really removed, but the one you see on the right is from Greenland, where you see that they're mostly open and there's a liquid water sitting within them. These are very important, not only because of the energy balance, but also because, as the image you see on the left of the tardigrades, are the only places where life is evolving on the Greenland ice sheet. And this is exactly why we're measuring their properties, both to understand the nature of the evolution of the biological material, but also to understand impacts on our planet, but also to understand how this information can be used for exoplanetary studies, in this case, Europa. But we had a project to look on Mars, and we were not able, again, to find anything relevant for on our side. But again, the idea is to look at the Earth and study understanding these ecosystems for understanding the impacts on the melting of Greenland, also to provide some Earth ecosystems framework that could help understanding the similar features on other planets. How they were formed, I mean, how did they create? The coal rock, cryoconite means literally coal rock. And it was first named by, Norskjöld in 1870. And these are the original images of the material that he took during his trip in 1870. And it's basically is made by these granules that can, and filaments that can evolve depending on the structure, depending on the input, and depending on the location of the cryoconite. But just to make one thing clear, cryoconite holes and cryoconite is pervasive on all glaciers worldwide. This is not something that happens only in Greenland or Antarctica, but we care about it, again, for the energy balance processes and for the absorption of the solar radiation. How do they form? It's a very simple process. The dark material creates more absorption of solar radiation, which helps this material to start sinking into the ice. As the material sinks, you have both the vertical and horizontal development. The vertical is because the material keeps getting the energy from the sun and keeps being warm. At the same time, there's a lateral development due to the incoming radiation from the different angles. And once, these angles, once the hole is saturated, there's no more energy reaching, or the energy balance is not, the energy provided by the sun is not capable to melt more the ice, then you have the consolidation of the cryoconite hole. This is how things look like. This is how a cryoconite hole, a lid with the bottom of, this is from Antarctica. These again are also from Antarctica. They are very interesting for a lot of reasons, because also they are never open for very long periods, and still you have an evolution of bioactivities there, or again, algae and bacteria. And it's very interesting for exoplanetary studies. On the left, I put some of the mineralogy that is mostly common that we found in a comparative analysis between Greenland and Antarctica. And you can see that mostly quartz and feldspar and other material that is, clearly due to the local deposition. This is how they look like. On the top left, and the top right, they are basically new holes. They can become larger, as I was mentioning to you, and deeper. On the bottom here, as you see, you also have the merging of the holes. So once the two holes get, like in this case, they get close to each other, they start merging, and they start forming these larger holes, which then at some point lead to larger puddles, as I show you in the picture. This is an interesting work that by Nozomu Takeuchi, who has been working on cryoconites for a very long time in Japan. And they have a time series of images on how the cryoconite holes evolved. You can see here, for example, on day 208, there is a first collapse in which different holes, they tend to get together. And it's very remarkable that they were able to capture this. And then you have, again, the deposition of snow on top of them that starts to mute the effect of the albedo. But why is this albedo important, and why do we care, and where do we care? If this is the west core part of the Greenland Ice Sheet, you can see this very dark band, which is exactly due to the presence of cryoconite holes and the development of biological material, mostly algae in this case. And the albedo in this case, which is, of course, the capability of the Greenland Ice Sheet to reflect solar radiation. So the lower the albedo, the more heat is absorbed and the more melting is produced, has been decreasing over the past decades by a value that is about 10% in a decade. And this is extremely important because, of course, the darker, again, the material, the more solar radiation is absorbed, the more this can create melting. The spectral properties of the cryoconite, of course, are driving this change in the albedo. On the left side, you have a work in 2010 by Carl Bogild, who shows that basically in the surface cryoconite and the cryoconite basin, they have a much lower reflectance than soil and natural surfaces, which promotes, again, more absorption. And also this work, again, by Takeuchi in 2017, if you look at the right here, you can see the pale bars are showing the mineral particles reflectance. The dark one is the one of the cryoconite. And the idea here is that, of course, the reflectance of cryoconite is much lower. The reflectance of cryoconite is much lower than the one of just mineral particles. And this is due to basically to the presence of humic substance that is reducing further the albedo from the one of the minerals. So in reality, the story here is that there is a combination of minerals that already tend to lower the albedo and biological activity, which further reduces the albedo, that play together and contribute to the overall reduction of albedo and promote further melting. However, I wanted to point you to a study that came out past year recently, and this is an image from the authors, in which they found out that there are huge, algae could be actually giant viruses could be, a reason why instead of reducing the albedo, these viruses could help to actually remove some of the algae. And so there is a counterbalance effect. And this is the first time I hear something that is looking at the process that it goes in the opposite direction rather than reducing the albedo. And this is a very interesting study. I am not aware of anything else that has been looking into in this regard. And of course, you understand the difficulties of characterizing both the biological spectral properties at this kind of scale is very complicated. Why also is it, and just I wanted to link now at this point with the Zibi's talk about remote sensing as well. We have very little clue or no possibility to detect properly algae evolution over the Greenland Ice Sheet with current remote sensing systems. If you look on the right side, which is a reflectance spectrum and from a sensor from the OLCI, which is basically a sea sensor looking at the oceans, the place where the spectral band is very narrow in order to for us to detect the presence of algae. These kind of capabilities are totally absent in current remote sensing observations of Earth. And there is a very little hyperspectral data, which will be very helpful over Greenland. There's actually more hyperspectral data in Mars, over Mars, than in Greenland. So currently, we are very blind about the possibility to explore the evolution, both in spatial and temporal ways of algae over Greenland, and this is creating huge limitations for us to understand the processes driving both the interaction with the mineralogy, the impact on surface melting, and of course, how the different biological process can impact on the melting of Greenland. I just wanted to close with a couple of references, and of course, 15 minutes feel like very short, and I'm happy to follow up with anyone and taking questions. But there is I put a mistake here, but we created a literary review on Cryoconite, which you can find, and I can share with you the link. There's also a very interesting review that came out in 2024 here on environmental research. Otherwise, you're more than welcome to look at the book I wrote a while ago, which also talks about cryoconites and puts more interesting stories about the ice. And sorry for the self-advertising, but I felt this was a good audience to spread the word. I wanted to thank you. This is an image, and I wanted to leave you with an image from within the Cryoconite hole from below that somebody took. I found pretty fascinating. And I'm going to leave the stage to Zibi or to questions, and I'll leave Shannon to decide. Thank you so much for having me and for inviting me.
Thank you so much, Marco. Let's give Marco a virtual round of applause. We do have time for a quick question. If someone, Karina is on the ball, so we'll take that one first. Karina asked in the chat, could PACE hyperspectral data be useful for making some of the characterizations that you were looking for at Greenland?
I guess so. I think it depends on I'm not familiar with PACE for the temporal resolution. I know that they have a good spectral resolution, but sincerely, to be honest, since we ended up with our exoplanetary work on Mars, the postdoc, who actually was one of the authors, Suji Wang, I think she also presented with you. I saw her name the past year. When she left, I wasn't able to find anybody else to look into this, but I'll be looking into this, and I'm really looking for any other input people could have in this regard. But thank you for the question, Karim.
Awesome. Well, thanks, Marco. Well, any other questions coming in for Marco, we'll let you stew on them. You can drop them in the chat or save them for the end. We'll move on to our next speaker, who is Dr. Elizabeth Turtle, or Zibi Turtle, a planetary scientist at the Johns Hopkins Applied Physics Lab. Her research combines remote sensing observations and numerical geophysical models to study geological structures and their implications for planetary surfaces, interiors, and evolution. Dr. Turtle is the principal investigator of the Dragonfly mission to Titan and the Europa Imaging System for the Europa mission, an associate on the Cassini Imaging Science Subsystem and radar teams, and a co-investigator on the Lunar Reconnaissance Orbiter camera. Zibi, take it away.
Thanks so much, Shannon. And I will just confirm, oops, oh, full screen mode, that you're seeing the slides.
Yep, thanks.
Excellent. I too wanted to thank the organizers. It's great to be able to talk with you here today, and I really like the pairing of people with in situ experience with this kind of environment with the discussions of future spacecraft observations. And it was great to meet you and learn about your really fascinating work, Marco. Thank you. I also wanted to say that our hearts are with our colleagues, friends, and families in Southern California, and that I hope everyone can stay safe during the terrifying wildfires right now. A lot of our team members are affected by these events, and I just hope everyone's able to be safe. So I'll talk a bit about Europa Clipper, just give a very brief highlights of the mission, and then I'll talk more about ICE and what we're going to do with ICE at Europa. I do want to highlight the number of people that worked on just the cameras alone on the Europa Clipper mission. All of these missions are really human endeavors. They involve a lot of people, and there were almost 1,000 people who have worked directly on ICE over the last more than decade now, as we've designed, developed, built the cameras that are now flying on the Europa Clipper spacecraft. The spacecraft itself is a large spacecraft. I expect most people here are fairly familiar with it. It's a solar-powered spacecraft. You can see the large solar arrays, large magnetic boom that was just deployed last month. The spacecraft has a suite of, there's the spacecraft itself. You can get a better sense of the scale. There's a person here in the clean room. This is the high gain antenna on the spacecraft, and the instruments are most of the instruments, many of them are on the nadir deck here on the platform that'll point at Europa during our flybys. There's a suite of instruments. There's a number of remote sensing instruments ranging from the ultraviolet through the thermal infrared and then into radar sounding wavelengths. And then there are a number of in situ instruments that will make measurements of the environment around Europa during the flybys, and of the magnetic and particles and fields environment around Europa itself during the tour at Jupiter. This is just a map of the orbits around Jupiter. So Jupiter's here in the center. This is Europa, Io, Europa, Ganymede, and Callisto's orbits. Most of the orbits of the spacecraft have closest approach near Europa, of course, because that's the focus of the mission. And we do more than 40 flybys of Europa. And those are designed to be globally distributed. So by being in orbit around Jupiter and doing these fast flybys of Europa, we minimize the radiation dose to the spacecraft over time, and that allows the longer mission and allows us to build up this global network of distributed flybys around across Europa, which gives us a really good global view of the moon itself. As Shannon said, we launched in October, so it's really excellent to be on our way. At this point, all of the Instruments have had their first checkouts, and I said the mag boom is deployed, the solar array is deployed right after launch actually, and the radar antennas have deployed. So that many of the deployments have occurred. Others are upcoming as we go through cruise toward Jupiter. The spacecraft doesn't arrive at Jupiter until April 2030, and then we start our Europa flybys about several months after that. So we have to be patient, but there's actually a lot of activities, including calibration activities that we'll be doing during cruise. So I'll dive more into what we'll be doing with the Europa Imaging System. The mission's goal itself is to explore Europa to investigate habitability. The cameras have a wide range of objectives related to understanding Europa's geology, the geologic processes that have formed its varied and in many cases unique landforms, as well as searching for recent activity, and also evaluating aspects of the ice shell itself to constrain the thickness, for example, of the ice shell, Europa's shape and rotation state, and to support geophysical measurements of Europa as well. There are a number of challenges with a mission to Europa, especially doing these very fast flybys. The geometry changes rapidly, and at closest approach, which gets down to 50 or even 25 kilometers altitude, the ground speed can be 4.5 kilometers a second. So these are, very different, imaging environments as you go through these flybys. And so we have a pair of cameras, a narrow angle camera and a wide angle camera, to be able to work together with this rapidly changing geometry. We actually have very large format detectors. It's not large for our phones these days, but 8 megapixels is pretty big for a planetary camera. These are 2K by 4K detectors. They can perform very rapid readout during the flybys. The cameras also both have 2 imaging modes. We can do framing imaging and push broom imaging. I'll talk some more about how that works. And this allows us to build up coverage of Europa at different scales and under different illumination conditions. The narrow angle camera is actually mounted on a 2-axis gimbal. This can point plus or minus 30 degrees in the along track direction and the cross track direction. And this actually allows us to use the narrow angle camera to build up global mapping coverage of Europa. Just some specs here of the cameras, and I'll put a link at the end to a paper we just published that goes into all the gory detail about the cameras if you want more information. The narrow angle camera has a 10 microradian IFOV, so this means at 50 kilometers altitude, we get a 0.5 meter pixel scale, and with that wide format imager, we can do imaging scale across a 2-kilometer wide swath. And with the ability to point using the gimbal, we can actually do stereo imaging at closest approach that is at a scale of 4 meters spatially and better than 1 meter vertical precision. So that's going to be really exciting data set over very small parts of the globe of Europa. The wide angle camera has a larger IFOV by a factor of about 20. We still get quite good coverage at closest approach at that 50-kilometer altitude. It's 11 meter pixel scale. And the wide angle camera is able to do push broom stereo imaging during the flybys. I'll show you a little more about that. This is just some images of the narrow angle camera here. Here it is on the spacecraft nadir deck. And then this is the wide angle camera and a closer view here. Just to give you a sense of scale of the cameras, this is the wide angle camera during our vibration test a few years ago now here at APL. This is the narrow angle camera, just to give you a sense of the scale and also the gimbal motion. The camera, this is really allows us a lot of flexibility in building up coverage of Europa, this having independent targeting from the spacecraft. So the detectors, as I say, are 2K by 4K. On each camera, there is a framing area that is just clear filter effectively. And then we have stripe filters at the edge of the detectors in both cameras. And so these allow us to do push broom color imaging. These are, I'll show you the wavelengths in a few slides. But this allows us to, when we're doing push broom imaging, build up color, 5 or 6 color imaging, as well as doing the framing observations. The framing is what we use to do the global mapping. This is a kind of point and shoot camera. We use the gimbal to target the images and then take images. We're not doing motion compensation or anything like that with the gimbal. We're not imaging while we're moving the gimbal. And we can use that to build up mosaics the way we typically do imaging. And with the narrow angle camera, this is the coverage that we build up through the nominal mission. We do get imaging at the higher altitudes, just not at the same resolution or the same illumination. But we will have global imaging, and then at better than 100-meter pixel scale, we'll get more than 80%, actually quite close to 90% of the surface. So this really will revolutionize our view of the surface. The push broom imaging, this allows us to use either the spacecraft, to use the spacecraft relative motion to Europa, like HiRISE on the Mars Reconnaissance Orbiter, and we'll build up with the wide angle camera in particular swaths along the ground track. These swaths will be in stereo as well as color. But you can see it's a much narrower kind of swath than what we're able to build up with independent targeting with the narrow angle camera. These are the filters that we have. The cameras are sensitive from a little short of 400 nanometers out to a little longward of 1 micron. And they have the same filters, but the wide angle camera is a refractive design, and so it doesn't have nearly as good sensitivity at very short wavelengths. One of the things that we'll do, the spacecraft is going to do as we approach and then recede from Europa, is do scans across the surface of Europa. And so we can use these to build up color images, again, using the NAC at a few 100-meter pixel scale, but in 6 colors. And so that'll give us a great view of the surface, and being able to do that on flyby after flyby after flyby will build up this great photometric data set, as well as being able to look for short-term change detection. I mentioned the stereo we can do with the wide angle camera. The field of view along track is 24 degrees. And so that's wide enough that by taking images with the forward, middle, and aft lines, as we do push broom imaging over the surface, we can build up 3-line stereo along that entire swath. And then this is just a graphic showing how we build up high-res stereo coverage with the narrow angle camera as well. Of course, these will be very small postage stamps on the surface of Europa. So we have, as I said, a really wide range of scientific objectives with ICE. One of them is to look for the possibility of recent or even ongoing activity. We have a number of ways of doing plume searches. This, of course, is Enceladus. But a good example of high phase angle observations and how plumes that have water ice particles can show up very well in those. And so we have a series of observations over the course of the mission of the limb of Europa at high phase angle. We also, and this of course is also not Europa, this is Io. You can see a plume here on the terminator, but on the limb, but there's also a plume standing up here above the terminator. And so that's another set of our observations with ICE, is to look down at the terminator and see if there could be any active plume standing up above it. Another way to look for activity is to look for changes. We actually have a few decades now between the upcoming arrival at Europa of Europa Clipper and the Galileo observations, and even further past the Voyager observations. Galileo had pretty limited coverage, but nonetheless, we'll be able to do change detection in those areas. This is the Galileo imaging coverage at different pixel scales. Galileo actually imaged less than 15% of Europa at better than 900 meter pixel scale. So we're really going to change our view entirely of Europa by being able to get almost the entire globe, 90% of the surface at better than 100 meter pixel scale. It's really gonna revolutionize our understanding of the geologic processes going on Europa, and how these features are related to each other and how they interact with each other. Just to give you a sense of scale, this is the surface of Europa from Galileo at 54 meter pixel scale. This is one of those chaos regions of Europa where these plates have broken up and moved around on some sort of matrix. This is the scale at which we'll get more than, coverage of more than 80% of the surface. So it'll really improve upon our understanding of the geology of Europa and the distribution of these features and their interactions. This again is at about that same kind of pixel scale, and we will have color at the same resolution, which will be excellent. Galileo was more limited just because of the data volume, and so we'll be able to have native high resolution color observations as well. This of course is very enhanced, but there are differences in the materials on the surface of Europa, and it'll be really interesting to understand that. There's a near-infrared spectrometer, imaging spectrometer as well, and we actually overlap at our longer wavelengths. They're sensitive down to about 800 nanometers, so our longer wavelength filters will overlap really well with the MISE instrument, and that'll be a spectacular comparison. Just kind of zooming in, we'll get about 30% of the surface at this kind of 10 to 25 meter pixel scale, where you can just see the complexity of these interactions between different geologic features. And then getting down to even higher resolution, we'll have a few dozen sites at better than 10 meter pixel scale. Galileo got maybe 5 images at this scale. So this will really show us a lot of differences of the surface at very high details. And then we'll get down to images that we've never seen an icy satellite, at scale of which we've never seen an icy satellite. So this is Earth, something Marco is much more familiar with than I am. But this is a GeoEye image of Antarctica at 0.5 meter pixel scale, which is what we get with the narrow angle camera at 50 kilometers altitude. And then just to put that in context, this is the same, these are now at the same scale. This Galileo image of a double ridge on Europa is now at that same scale. So we'll really get to see something we've just never seen the surface of an icy satellite at this scale before. And it'll really be illustrative of the kinds of fine scale surface processes that are occurring. Just to wrap up, I give you a little more context of how the instruments fit together. The wide angle camera field of view is shown here in green, and this little blue box is the narrow angle camera field of view. And then they're all kind of co-boresighted together. Our ultraviolet, near infrared, and thermal infrared instruments, all of which have about the same pixel scale as the wide angle camera. So these are going to be really excellent complementary data sets that we build up through the course of the mission. So just to finish, and I can put these in the chat as well, but there's a link here to the collection of Space Science Reviews papers that have just been completed about the Europa Clipper mission and the instruments, and a link to our ICE paper in that collection. So I'll wrap up there, and hopefully there's still time for some questions.
Thanks, Zibi. Let's give Zibi a round of applause as well. You had the honor of getting to introduce us to Clipper as well, so thanks for doing that. Do we have a question specifically for Zibi? I see Jason Hofgartner left one in the chat. How do these filters compare? How do the ice filters compare to those on Galileo and Voyager?
So we actually tried to use about the same bandwidths as the Galileo, as some of the Galileo filters. Galileo had more, had broader science objectives. Were focused on Europa and understanding its surface. But the filters that we have were intended to try to match as well as possible that kind of wavelength range of the Galileo filters, the Galileo SSI. And I don't have it in the figure, otherwise I'd go back to it. I don't have the Galileo bands, but we should get that a comparison figure back together. We had one originally, and should reproduce that now. So thanks for reminding me of that, Jason.
All right.
Sorry.
Yeah, go ahead.
There is a question about Antarctica plot by Alexei.
Yes, I was going to say, let's go ahead and open it up for questions from both of our speakers.
Okay, I just wanted to be sure because there is a comment on the Antarctica plot.
Mm-hmm.
Yeah, there is a nice loss change in 2022. There are two reasons for that. The first one is that there are two different sensors that are looking there, and there was a gap between, for about 6 to 8 months between the GRACE satellite and the GRACE follow-on, which is the second one. But also Antarctica is much more variable because the accumulation patterns can really play a large role in some of the outside regions. And the mass redistribution by wind blowing is also another factor that drives a lot of the mass change. So what you see in there is overall Antarctica, you have some changes in trend, but overall on the West Antarctica, this is less noticeable.
All right, I'm going to use the chair's prerogative to ask a question to both of our speakers. Marco, you had mentioned that the cryoconite holes fill up pretty quickly, and that you see changes in their morphologies on quick timescales. And Zibi, you had also mentioned that one of the primary science goals for ice is looking for changes at the surface. So my question to both of you are what kind of timescales you are looking at, and what the drivers for those you expect those timescales to be. What drivers you expect?
Right, and in the case of the cryoconites over Greenland, that's a great question because we really have little information about how they evolve, and most importantly for us, we have little information about how much of the material is splashed out during these big melting events versus staying there. So I don't think anybody has calculated the age of the material in cryoconite holes. In Antarctica, it's very different. They remain sealed for a very long time. They don't remain uncovered, so you can assume that the material is there for a good amount of time. But in Greenland, it's very dynamic. I would say that once the holes they reach a point that are big enough and deep enough not to be impacted, they become mature. Then their evolution, the time scale is much slower. However, it's still not clear, I think, if you have multiple cryoconite holes or one large hole, what is the overall effect? So in general, the evolution of algae and the presence of these cryoconite holes is probably repeating every year in the same location, similar locations, but the effect is strongly linked also to the feedback mechanism that more water can provide more material for the algae and the biological material to evolve, and therefore there is this feedback mechanism that we are still not sure about how they're driving it. So if I have to make a guess about how often we would like to monitor those, even if we will have weekly or even bi-weekly measurements and the capability of observing a multispectral, or at least in that band where the biology is very the reflectance is sensitivity to biology, that will be a huge game changer for us.
That's really cool. So we'll be looking at rather different timescales. We don't actually know how geologically active Europa might be. We know from the fact that there are not a lot of impact craters comparatively, that it is geologically, the surface is geologically young, and there have been some tantalizing hints of possible plume activity that we will be searching for as well at Europa. But for us, really, the timescales are driven more just by the nature of the missions. So, by comparison to Galileo, which was at Jupiter around the turn of the century, and Voyager, which was there a couple decades before, to 2030, those are the timescales that we'll have to be able to look for different types of changes on the surface. And then during the mission, we'll have a flyby every 2 or 3 weeks, but not always over the same part of Europa. But nonetheless, we'll be able to, especially in those, those global views that we have on every flyby as we approach and recede from Europa, but in comparison to those, we'll be able to look for larger scale changes at the, few 100-meter scale, which you wouldn't necessarily expect unless you have something dramatic like a plume over the timescale of the mission of a few years. The mission duration is about 3.5 years. So the timescales really will be driven by the nature of the missions rather than the nature of the geologic features, but they should give us insight into how rapidly mass wasting or possibly endogenic activity might be occurring, or at least put constraints on that.
Thanks. I see a hand up by Jason Hofgartner. If you want to unmute and ask your question.
Yeah, thank you both for your talks. They were very interesting. My question is for Marco. Marco, if I heard you correctly, you said that this cryoconite holes were the only place on the Greenland ice sheet where life is evolving. I was just wondering if you could explain a little bit more what you meant by that. Like, is this the only place where we see life that's alive on the sheet, or are you seeing an evolution that you're referring to, in modern climate change days or that sort of thing?
Yeah, well, I was referring to the fact that often people associate life in Greenland with polar bears and with Arctic terns. When we were camping on Greenland ice, we were 60, 70 kilometers inland by helicopter. And so we were visited by an Arctic tern regularly. That was the only guy who was maybe up there. And recently there's been polar bears visiting up to Summit, which is in the center of Greenland, up to 10,000 feet. That's why they had to move out now. The tents of people sleeping there, they all have to sleep in the big kitchen tent because they found basically a polar bear sniffing on somebody's tent. And the only reason why this didn't turn into a tragedy because one of the guys from NSF working at Summit was smart enough to open a can of oysters and throw it on the opposite direction. The polar bear ran there and the guy in the tent was able to run inside. But what I was referring to is the fact that in reality, if you exclude these visitors, that is really the only, the Cryoconite Holes is the only place where you have evolutional life, where you have tardigrades. You can cook them, you can freeze them, you can smash them, they'll still be there. And also you have this kind of bacteria, autotrophic, heterotrophic, and different conditions to survive there, which again are probably the closest thing to what we can imagine could be exoplanetary life in terms of conditions on Earth. And this is very much more true for Antarctica. There is a very long study for LTR, for the Long-Term Ecological Research Observatory in the dry valleys, where I work with Christine Foreman from Montana State University. But in general, if you are thinking of something alive that is born, breathes, or so to say, and dies there, that's actually what the Cryoconite Holes for me are the only place where life can survive and is present on the Greenland ice sheet.
Great, thanks for clarifying
Thanks
that.
for the question, Jason.
Can I ask
Go
a
ahead,
question,
Chris.
Shannon?
Yeah.
So my apologies if this happened in your presentation, Marco, and it went by too fast. But a question maybe for both of you is, there's this hemispheric difference in albedo on Europa, right? There's the side that's covered in sulfur, we think, or the brown staining that seems to be very much on the trailing edge. Although it's going to be way beyond the resolution of ice, is it something that you think we should be thinking about? Is whether cryoconite, could the instance of photons from sunlight on the different materials, darker and lighter materials on the surface of Europa be sufficient at that range that the same cryoconite effect could happen?
I think, if I understand probably the question, you're asking if the conditions that we have on Earth can be somehow translated or envisioned to be valid on Europe.
Yeah, I mean, because if the main reason is the
Difference in albedo.
competitive, yeah, so it's like a difference in the
Right,
ability to absorb radiation, solar radiation, right?
Yes, yeah. I to be honest, I have no clue. I don't know, because I think I was going to ask Zibi if she actually thinks there could be some cryoconite there, at least the mineralogy. And I don't know. I mean, when she was showing the 1 meter or the 6 meters, I was like, oh man, we can try to look into those patterns now. We can try to use some multispectral ratio to see if there is some patterns. I would start, to be honest, from a morphological analysis to see if there is something that resembles cryoconite and they have similar spectral, potentially similar spectral signatures. But again, the only problem that we have in Greenland is that, again, beside the suggestion by Karina about the pace, I'm not familiar of any hyperspectral or multispectral data that can be used on Greenland even to characterize these kind of things from a general perspective, if you don't go there and use the hyperspectral sensors. That's what we do. And there is a big group in the UK called a big project funded by the NERC, Black and Bloom, that we're looking at exactly this. But imagine how difficult can it be to measure the hyperspectral properties of algae or bacteria into this material, and then you have to add all the mixed effect of the footprint. So I in this regard, working together would be at least understanding whether there could be analogs, and if so, from a morphological perspective, what can we learn from the spectral data that the mission Clipper is going to collect, and how do we translate that on the ground in Greenland so that we can then in turn go back to other missions and analyze even previous data. Sorry, Zibi, I don't know if you want to add something.
No, that was a much better answer than I will have. I don't know what we will find at Europa in in that vein. There certainly are albedo differences, and one of the things that I think the suite of instruments we have on Europa Clipper will be good at kind of teasing out is that comparison of like morphology, with and the relationship to different spectral characteristics, et cetera. We won't have high resolution in the range. I think that's most important for that Marco was showing. The high resolution will be at shorter wavelengths, and then into the near infrared. ICE only has the broadband filters. So I think we'll get tantalizing hints of some of this and the interrelationship of the materials and the properties of the surface at these high resolutions, or the properties of the surface at at fine scale. But I don't know if we'll be able to answer that question definitively.
Does Clipper already have an instrument to measure the photon flux of what's coming in from the sun, or is that already known anyway?
I'm sorry, the photon flux
from sunlight?
So we will build up albedo maps. So we'll be able to do that. Our radiative calibration is about 10 to about 10%. And then of course we have these different wavelength data sets to be able to do cross comparisons and things like that. So we will have that kind of constraint and much better understanding, I think, of the global albedo patterns and how those relate to the specific geologic features. And something I didn't talk about very much, if I can speak just for a little longer, is the radar instrument is a sounding instrument. And so that will give us insight into the vertical structure of the ice shell. And so by having that, this surface topography that ice will be able to measure, limb profiles that will get that, you know, the long wavelength shape of Europa, and then combining that with that subsurface structure, we'll really get a three-dimensional understanding of some of the processes at work, and being able to tie that to the nature of the surface, I think will give insight into the kinds of things that that Marco was talking about as well.
Well,
Thank you.
thank you both so much. And Chris, that was a fantastic question to end on. So thank you for asking that. Let's all thank our speakers again for answering the very difficult task of speaking about their science in 15 minutes. I really appreciate you taking it on and doing it so well. You've really set the stage for the rest of our lecture series. Thank you all for tuning in today. I apologize for us going a little bit over, but we had a little bit of a late start. This recording will be posted on our YouTube channel for you all to refer back to later. And we will see you in February for the next instance of the Not So Quarterly lecture series. Thanks, everyone.
And thanks,
Thank
Shannon,
you.
for organizing and for being such a great host.
Yes. Thank you.
Take care.